Imagine you're going to buy a used car. You found one listed for 18,000. It looks clean, the mileage seems okay, and the owner is telling you it's a great deal. But how can you actually know? Maybe it's worth 14,000, maybe it's worth 22,000, especially if you're like me and know nothing about cars. That's what made me think, can I build an AI to predict the car prices? And that's exactly what I did. But there is one small problem, I need the data. A lot of it. And not just any data, local data in my country, because car prices may vary a lot between countries. That's why I scraped my own dataset. I scraped the biggest car listing websites and mobile apps in my country, and I got a total of 18,000 listings. With the data I had, first I had to normalize all the datasets I got from different apps into one spreadsheet, with all the fields having the same structure. And now we start the fun part, the machine learning part. First, we load the CSV file in Python. I wanted the years to make sense, so I filtered out any year below the 1950 and above 2026. Why? Because if a car contains a Mercedes from 2035, it's probably wrong data and not a revolutionary car. Next, we should fix the mileage. Some cars had really suspicious mileage. When you find a car with 50 kilometers or another car with 1 million kilometers, these numbers can really mess up the machine learning model. I decided anything below 1000 kilometers will be deleted and anything above 500,000. But now we have another problem. A lot of the sellers don't list the mileage of the car. If we want to delete all the records where the mileage is empty, we will end up with half of the data. Therefore, I replaced all the missing mileage with the average of its year. For example, if I have a Mercedes 2018 and I don't know the mileage of it, I just look up the average mileage of cars in 2018. It may not be accurate, but it's way better than throwing away the data. In this step, we should check how many null records we have in this data. This is one of those steps that might look boring or repetitive, but it's actually extremely important. Same with removing duplicates. The exact same record may appear multiple times in the dataset, so we just delete the additional records. Also, we should not forget to filter out the price, because a car listed for $20 is definitely not real. The same applies for the extreme expensive cars for $2 and $3 million. I removed the extreme values and the outliers from the set. Now our dataset is clean, but we still have one more problem. Regression machine learning models do not understand text, so we use something called one-hot encoder. This basically transforms the categories into separate columns. So instead of having model equal Toyota, we will have a new column called model Toyota. Now that everything is set, we should decide what are our features and what we're trying to predict. So here we're obviously trying to predict the price, and our features are the model, the location, the mileage, and the year. Now it's time to train the model. Usually in machine learning, we don't train the model with the entire dataset. So I split the data into two parts, 80% for training and 20% for testing. For the model, I started with something simple, linear regression. The model tried to learn relationships between the features and the price. For example, newer cars tend to be more expensive, and high mileage tend to reduce the price of a car. Linear regression tried to combine all these relationships in one mathematical equation. It's a great baseline, but used car prices are not always linear. 2015 Toyota Corolla and the 2015 Land Cruiser don't tend to lose the same value with time. A car with 100,000 mileage is not necessarily worse than a car with 15,000. I used two metrics to see how well it performed. The first one is the mean absolute value, which tell me how much of the model was on average with the prices. The second one is R-square. This tells me how much invariant in car prices the model was able to explain. The recent weren't actually amazing. The mean absolute value was $10,000 and the linear regression is 0.3. The perfect value is 1. This is where things got interesting. I switched to XGboost. Instead of trying to fit everything in one equation, XGboost actually built a collection of decision trees. Think of each tree as a collection of questions. Is this car newer than 2018? Does it have low mileage? Each tree make a prediction, and then the next tree try to improve on the mistakes that the previous tree made. It keeps going again and again. That's the basic idea of XGboost. Finally, and tested it, and the results were... Now those numbers aren't perfect. In fact, they are much more than I intentionally expected. It's actually a really decent result, because this is the reality of working with real data. Here I'm working with asked prices and not the actual value. Some cars may be in much better and much worse conditions than others, and I'm only using few features to make the prediction. And if you enjoyed the video, don't forget to like and subscribe, and tell me in the comments ways to improve the model and improve the data collection pipeline. That was it for today. Bye.